started, hopefully getting close to the way through quadrature. The next homework is going to be about differentiation in quadrature, and it'll be available to you tonight or playing at midnight. And it'll be due at the same time, Thursday, 11:59. I believe that's the last thing we're going to do before the midterm. So all the material up to quadrature and finite differences is going to be fair game on the midterm. We're, depending on how much time we have, we will spend some time getting into ODEs, solvers, but that will not be on the midterm. Have a little bit of time to do the homework. You'll see the solutions of the homework before you actually have to do the midterm. I also will make available a set of practice midterm questions, which I highly recommend you do. We will spend some time in class going over some of those solutions, so we can talk through them. That's the basic idea. Or we get into
than the homework.
hard for who? Oh, yes, it is.
Put it on.
Huh, I just see
It's a battery?
thing.
Oh, that's
Oh, so
fine.
that's good.
I
All right,
must have
cool.
just hit it. Yeah, sorry.
Like the homework's like
Yes.
is
Yes. It's going to be 50-50, but it's going to be shorter than the homeworks. Easier questions. Kind of. Shorter questions. Maybe that's a better thing I should say. Did you have another question, or was that as a follow-up? No, the intention is for, okay, so the intention is that you could do it in a day. You have 4 days. So you can use that flexibility to do it when you want. And if you want to spend more time on it, please feel free. But other than that, it's actually just like the homeworks, just shorter. Yeah. No. What I would encourage you to do, I actually don't know if I can do this for Campus Wire. We will not, you can send anonymous and direct questions on Campus Wire. We will answer those. You can also just email us. But there will be office hours on Friday because it's just the normal time. But by and large, it doesn't really work when it's an exam where you have to be by yourself. So it's just awkward. So if you do have questions, we will try to answer them as best we can. But yeah, it's going to be, this is all individual. So yeah. I don't know yet. That's exciting, isn't it? I would say 3 to 4, but again, they're going to be shorter questions than which are on the homework. F, G. How far have I gone? This A, B, C, D, E. Oh, the next homework has more. Yes. You will get it Friday morning at midnight, and you'll have until Monday at 11:59. So those are your 4 days. You have Friday, Saturday, Sunday, Monday. Any other questions? Oh, I kind of have a question for you. So if you have any conflicts, please let me know now. Do not let me know on Thursday before the exam. Obviously, things come up. I understand that. But if you do have a conflict that you know, please let me know as soon as you can so I can make alternative arrangements. Yeah. In what sense? On Monday you have an exam? Yes. I will have to talk to Don about that. Okay. We'll try to figure it out. How many of you are taking 4200 right now? A few of you. It's PDEs. PDEs in applied math. Okay. So only a few of you. All right. We'll figure it out. There was another question down in front here. Oh, yeah. Like it's midterms. Yeah. All on Monday?
Yeah.
What is going on? So, I'll get back to you. What I'm tempted to say is that you're getting 4 days to do a 1-day exam, and I know you have to study for multiple exams. But if I move it, it's going to cause havoc in other ways, and I'm sure we're going to conflict with someone's exams. So I will look into it. More than likely, because it's a subset of you, it seems, a smaller subset than the larger subset, that we will not move it. And I feel bad about moving it in case you actually planned on, only doing applied math over the weekend, and you don't want those plans to get ruined. So yeah.
No, that's the 22nd.
That's the week before.
Yeah. Oh, well,
It almost kind of seems like we actually conspire with each other to actually have our exams all at the same time. That's not true. Okay. I'll get back to you on all this. Any other questions? All right. I did want to say and clarify something because it's come up a few times, and that's the course grading scale. This course is not curved. You are not being graded against your peers. You are being graded based on a percentage range, which is the standard percentage range. It is now here for all of its glory. The only adjustments that are made is whoever does the best in the course, someone who never gets 100%, because that would be crazy. I usually just add whatever will take them up to 100% to everybody's score. So everybody gets bumped up for that purpose, okay? This is the percentage range. This is pretty set in stone. I would say most often the average of the course is in the high B plus range. It's very, very rare that anybody gets less than a C. It happens to a few people, so don't be one of those people. I am quite fine giving everybody an A plus though, okay? That would be fantastic. I'd feel much better about grading. I don't like grading as it is. So if you could work on that, that would be great. But this is what it is. I also want to mention that there are multiple ways that I do tend to adjust grades. I'm never going to adjust your grade down. That's not fair. I may adjust it upwards, like if you're right on the border of a grade and you've been consistently doing the homework on time and all that type of stuff, that might be reason for me to say, I'll give you like 0.01%. Usually I would do that anyways. Also, if you're participating on Campus Wire, answering people's questions consistently well, that's another good reason to do it. If you have improved over the semester, if I see the gradient is positive, that might be a good reason to also bump you up a little bit. So just keep that in mind. It's all at my discretion. I'm not going to say I'm going to do it or not do it. And also, please don't beg me to do it, because that won't make me very happy about that. But if you do have questions about your grades or anything like that, please come to me and I'll talk you through it as well. Okay? Any other questions? All right. So we were in the middle of talking about order of convergence. We didn't quite finish this. We did all the error kind of writing up here. But then we have these plots, which are kind of boring right now, in that they just are what look like lines. I've modified this a little bit. Actually, I've used log space instead of lin space to do, or actually range, to actually decide how many points to use. But the basic idea is that these are lines in log space, and that their slope, again, is going to be the order of convergence. Okay? So, I could actually construct a line through these points. I could use an interpolant of line, or do it at least squares fit through these points and say, okay, whatever the slope of that thing is my order of convergence. That's actually probably the most, kind of coherent way to do this. Oftentimes in this class, I just expect you to plot a couple lines for first order and second order convergence and make decisions based on that, because usually we are going to see pretty much first or second order convergence. So that's what I want to do here. And over here on the right, is kind of what we're doing. We have the error. It's dependent on delta x or capital N, depending on how you want to plot it. And we're modeling this error as some constant c times delta x to the nth power. When we do a log-log plot, it's the same thing as doing log on both sides. So the log of the error is going to be equal to log of c plus n times log delta x, which is an equation for a line, which is why we use the slope to determine what that little n is. Okay? So we just need to do that part. So in the notes, I often use this order. I create a function called order c. Actually, I'm just going to write a function in this case, just so it's a little bit clearer. So this is really just computing what the c is. So this is, if you don't compute what that c is, our lines that we're going to draw are going to be somewhere. So if c is large, we are going to have lines where they aren't so helpful. So this really just matches up so that one of the points we're going to choose, one of these black points, our line we're going to draw is going to start at that black point. That's all we're going to do. And so this function is going to take in a delta x and an error. And those are data points that we have. Usually we just pick the first point. And what this is going to return is just this formula here. So c is going to be equal to e log e, the error, minus n times log of delta x, which we just have. So we have the exponential of the log of the error value minus the order times, oops, I didn't do the order. Still need that. So order is just that n value in this case, times numpy.log of delta x. Okay, so this will return a number. So that what we're going to do is to each of these plots, we're going to add two lines, one that's going to represent first order and one that's going to represent second order. So we get delta x, because this is going to be a line, order c times delta x, and I'm going to pick the first point in all of these things just for ease of use, and then oops. The second one, I have to pick, this is basically what the y value is that I'm going to intercept with. So basically just lining it up again with that first point. I'm going to get rid of this now. Actually, I didn't want to do that. Oh well, we'll fix that a little bit later. And then I need to, I have to give it an order. So this is going to be a first order line. And then what I'm going to do is actually plot this thing. So times delta x to the first power, and then I'm going to do that in red, and I'm going to provide a label first order. So hopefully I did that right. Okay. So in the upper left-hand corner here, I chose the first point. My line is starting from there, and I'm drawing a slope equal to 1 downward. So you can see clearly in the L infinity norm, this is a first order method. Right? It's lining exactly up with that first order line. This other one here, you can see it's converging faster than first order, which is surprising because we didn't expect that to happen. Okay? But it's a different way to compute the error. Now you can see that something isn't going too weird, except that this is not converging at all. Right? It's basically flat. So something is definitely wrong there, or at least the error is not really telling us the whole story. And here, it's actually converging at something slower than first order. Okay? It is still converging. It's decreasing with delta x gets small, like that. So to change this to second order, we're just going to copy this. We change the order into the function order c, and then we change the exponent on delta x, and then remember to change the label, because I forgot to do that in the homework. So we're going to plot two of these lines. Oh, let's change the color, though. So in these top two plots, you can definitely see that in terms of whatever the error I'm computing here, it's lining exactly up with the line that's the first order line. So we would conclude that this particular algorithm is demonstrably first order. Similarly here, because this is lining up with the second order line, that this would be second order. Okay. So this isn't a proof. It's an experimental result that seems to hold out that these are first and second order. And of course, this is a complicated question. We see that, again, neither of these two are first order accurate. This one's converging, maybe at 0.5. We'd actually have to check that. And that one's not converging at all. Okay? Now, the other part of this is that these are all different ways to measure the error. We expected first order convergence, if you remember the actual results. So these top two are using the L infinity norm, which is using the maximum error. Just taking all the errors, and we're calculating it for a big vector, so a lot of different points. And it's finding the maximum and using that in two different ways. One way, scroll up here, is just using the normal absolute error, nothing fancy. And we see the error that we expect. And then this other one is a shifted business. So we're going to see why this might actually be, that it actually has to do with shifting in this particular function. See that in a little bit, why this actually turns into a second order method in this particular error. These other two are a little bit more complicated. The L1 and L2 norms are going to take the error of all the points and sum them together in some complicated way. L1 a little less complicated than L2. But if you remember, the statement we made about the error itself was that if I approximate the derivative at a single point, I get first order convergence to the correct error, or the correct answer. Here I'm adding up all the points and getting something less than first order, and actually not even getting first order in the L2 case. This has to do with the fact that we're adding a bunch of error together. And actually, we're doing enough of these points that we're seeing that eventually a bunch of error added together will equal more error, and it converges more slowly than if we were just looking at the pointwise error. So that's the key. Our statement was based on the pointwise error. Those last two are actually based on the sum of a bunch of error all added together, okay, which actually can introduce decreases in the order of convergence. Now there's ways to get around that called the grid norm, where we actually add the fact that we have a delta x kind of lurking inside of this. And we'll talk a little bit about that later in the course, but just keep that in mind. And I'll be very specific about what kind of error I want you to explore when asking questions about this type of stuff. So keep this in the back of your mind. Error is a difficult question. It's never quite clear sometimes what kind of error you want to explore, but it doesn't hurt to go explore a few of them. Sometimes L infinity actually is the worst one to do because you're doing a huge error in a particular corner of your problem, but the rest of it's fantastic. But the L infinity norm might actually tell you you're doing horribly, make you feel bad about yourself. Whereas the L1 and L2 actually might be great. Okay? So it is actually a complicated case-by-case problem to try to deal with. Okay. So any questions about this? All right. I closed my slides. Okay, so we've covered first order, forward and backward differences. The second thing we're going to do is second order centered differences. So a centered difference is a finite difference scheme that looks to the left and to the right, and it turns out if we use more points, like you might suspect, we're using more points in our interpolant, we get a higher order accurate answer. Okay? So in kind of the interpolation standpoint, what we can do is we can take a P2 interpolant of the function f. So we're looking at x0, x1, and x2 in this particular interpolant. But in general, we're going to have xn minus 1 and xn plus 1. So in my little diagram over here, if this was at xn plus 1 is over here, and this is xn minus 1. So, and we're going to approximate the derivative at this point, and so the point is in the center, hence centered differences. Okay? So if we do that, we do an interpolant, a P2, which means it's linear. So I have just an equation of a line here, or excuse me, P2 is quadratic. So I have equation of a line, and then I have this quadratic term. It looks complicated. However, this is just the interpolant. I'm going to take the derivative of this thing, as we did, and I'm going to evaluate it back at xn to get my approximation. So let's go through that. So here's the derivative. This is just the form that we had before. Here I'm using a Newton polynomial version of this. I can simplify this a little bit to this, and then I have basically the differences. If I plug in then xn to all of this, so note that I still have x's in places, what I get is something quite simple, actually. There's a lot of assumptions going into this. For instance, we are assuming that we have a uniform grid spacing. So the distance between xn and xn minus 1 and xn and xn plus 1 are all delta x. Otherwise, this does get more complicated. But basically, doing a little bit of algebra leads us to this. So it's f of xn plus 1 minus f of xn minus 1 divided by 2 delta x. Okay? Now, there's something interesting here. I started out using 3 points, and I ended up using only 2. In fact, of all things to leave out, I'm leaving out the point where I was actually interested in the derivative, right here. Okay? So this actually looks more like a secant approximation, so that's one way to think about this. I'm actually finding the equation of the line between these 2 points. Right? That's exactly what this is. This is the slope of the line between xn plus 1 and xn minus 1, and then 2 over delta x is going to be the distance between these 2 points. And that gives me a second order approximation, which I can show looking at the error. Okay, so here's the error. This is the remainder term. If I take the derivative of that, it's going to be this cubic business dependent on f triple prime, the derivative, somehow evaluated at c. The important point here, though, is that once we actually evaluate this thing at xn, notice that these are going to be xn minus xn plus 1, basically delta x. This is delta x. This is delta x, delta x, delta x, delta x. This is starting to look like a term that has asymptotic behavior that looks like delta x squared, okay? Which implies that the error is going to shrink asymptotically as delta x squared. Okay? So let's look at this a little bit more. Basically using those heuristics, basically adding, all these terms are just addition, so we're not too worried about that. We think delta x is going to be the dominant behavior because that's the thing going to 0. So all these kind of collapse down to delta x. We keep this term here because you never know. The third derivative of f could be large. And we say this is generally what the term looks like, and asymptotically it goes as delta x squared. Okay. So I'm going through this a little bit fast because there's an easier way to look at this as well. But we expect this particular method to be order 2, or second order convergent. So let's implement that. I can click. Okay, so we're going to implement basically the same thing using the same formula. I'm going to give you a minute or two to try to do that and see if you can get it to work. Basically, it's going to be doing the exact same thing as before. Don't worry about the edges, or if you want to, try to figure out how you can do the edges of this, right? Because if I'm looking at the derivative here, I don't have something to my left. In fact, I don't have something to my right over here, so I have to use something different at the edges of my function in order to get the approximation to work, if I have a finite number of data points. So think about that, but just try to write this up, and then we'll write it up together in both the vectorized form and the looped form, and then we're going to do some convergence studies. Okay, so I'll give you a couple of minutes for that. All right. So in the notes, I'm actually doing this in a vectorized form, but I thought I'd show you the loop form of this. So I've set up some stuff. We are going to ignore the 2 endpoints on the data. Still want to compute the derivative at those points. We're just going to have to do it a different way. But this, at least, is going to be not too bad. So we want, the actual formula we want to implement is, of course, this one right here. So we want to evaluate f at the point to its right and subtract from it the point to its left. And here, the way I've set this loop up is that I'm storing or I'm computing the derivative of the xith point, so that if I have xi, I don't need that, but I do need xi plus 1. And then it's fx hat I minus 1, and then divided through by 2 times delta x. Here, there are actually forward and backward differences that are second order accurate, but since we haven't talked about those yet, I'm going to do just the first order versions of these things. So if I'm using f prime hat 0, means I need to go forward with this. So that's going to be f at x hat 1 minus f at x hat 0 divided by delta x. And then similarly, at the other end, I'm going to have x hat negative 1. So that's the furthest right point minus the point to its left by delta x. So here we're using 20 points. So let's see if this is actually still. We use 20 points here too. Actually, let's try 10 points. So we see with 10 points, you can see there's definitely error. If I can scroll. Especially at this point in the middle here. So let's compare it to this one down here. Oh, I guess I counted differently. Let's try 11. So it's, it's getting better. Wait, am I executing the right one? Yeah, I am. It's getting better. In fact, actually, you can show that for delta x here and the error there, that it actually is going to be a smaller error. And that's just indicative of the fact that eventually delta x squared gets smaller faster than delta x to the first power, which is not surprising. There's also some issues. You could say, well, I actually am going to be incurring a first order accurate error on the edges, and that is a problem. So if we use the L infinity error, it's going to catch those as it gets smaller. But we can also do the same type of thing. So this is just a pre-coded error convergence study like we just constructed. And we can see even for the L infinity norm that we see that this is second order accurate. And it's not using that trick I did before. Okay? By the way, the trick we did before is based on the idea that if we look at this formula, there's a 1/2 delta x in it. And it's going to be looking like a difference, but it's a difference that's twice as wide. So the forward and backward first order differences, if looked at in a different way, is actually second order accurate centered difference. And we'll see why that is in a little bit too. But that's kind of the idea here. We can actually just shift the point that we think the derivative should be at, and we get a second order convergent method instead. This is for using first order differences. If I was using L2 here, so this is just switching the type of error I'm looking at. You can see, well, it's definitely not second order anymore. It's something in the middle, kind of what we saw before. I can also even change the edges. So these are the forward and backward differences that are second order accurate, which you can derive. And it doesn't really matter. So this is really the difference between a pointwise error and the fact that I'm summing a bunch of errors together. And we see that degradation in the error. In fact, if I actually change this to 1, hopefully this works. No. Oh, does delta x not actually be? Oh. No, that should work. So this is what happens when you try to come up with something on the fly. Doesn't often work. I don't understand why. Oh. Because I don't have an I. Okay. So by multiplying by delta x, that's the grid norm. If I actually include the delta x in there and I sum over the entirety of all the errors, that's actually where that comes from. And it's well known that that's actually how to compute. If you're going to use an L1 or L2 norm, multiplying by this delta x or inserting it into the norm is the way to get the correct expected convergence out of those. You can do it for L2 as well. You can't use lin-alg.norm because you actually have to insert the delta x inside the norm in a funky way. So this one's a little bit easier to do. Okay, so we've derived these things using polynomial interpolation. I actually do not prefer to do that because I find it tedious algebraically. Instead, I think that finding these things using Taylor series is a little bit easier. It's a little bit more constructive. So let's go through that. Here's the Taylor series of the function f. Okay? So we have done this a bunch of times. This is not evaluating at a particular point yet. But there's one thing I want to point out, and that's that there's an f prime of xn here. Now, we've never really used this thing, but this is exactly where we're trying to approximate. There it is in the Taylor series. So what happens if we can try to actually use the fact that we have f prime sitting there? Can we actually use that to our advantage? And that's kind of the idea behind a Taylor series derivation of finite difference method. So here we have this. We actually have to use the Taylor series a couple more times. This is the Taylor series evaluated at 2 different points. We're evaluating an xn plus 1 on the top here. Okay, so that's just replacing x with xn plus 1. And note that the second line here, so this is just delta x. Right? So, and I get delta x squared, delta x cubed, things like that. So that's the approximation of f at xn plus 1. Note that I still have f prime of xn in it, right? Because I'm centering my approximation at xn. Similarly, if I look back the other direction, xn minus 1, I get xn minus 1 minus xn, which is negative. So the difference between this and this is that I get an alternating sign, and that's because of this. So odd terms in the series are going to have a negative sign. Even terms are going to have squares to the 4th power and things like that, so the sign actually does not flip. Okay? So I have this series, I have this series. What I want to do is say, I want to approximate f prime at xn, and then plus stuff, which is going to be my error. And I'm going to say that I want an approximation that looks like the following. Something a, some unknown value a, times fxn plus 1, plus b times f of xn, plus c times f of xn minus 1. All right, that was our stencil. That's where we decided to evaluate this thing. I don't know a, b, and c yet. If I write this out, I plug in my f of xn plus 1 Taylor series, my f of xn minus 1 Taylor series. Note that I've written this suggestively, so this is still multiplying a, b, and c. And of course, f of xn is just f of xn. I'm fine with that. That just sits there. Okay, so what I want this to do is to be equal to f prime plus r, where r is higher order, has delta x's or derivatives that are higher. So I want these 3 terms to disappear. Right? I cannot have f in this, and there's no delta x's multiplying this, so that would be kind of disastrous. I want to keep this term, so I want f prime, delta x f prime minus delta x f prime multiplied by unknowns a and c to equal 1, because I want to keep that term. Then the rest is kind of whatever you want. We have 3 unknowns. We need 3 equations. So the third equation I'm going to use is to say, well, I don't really want f double prime to stick around. So I'm going to say this term times a plus this term times c. I want that to disappear as well, which means the rest of this stuff multiplied by a and c is going to form the remainder, that r piece, and is going to actually be exactly the leftover error. Okay? So note that I'm actually being very explicit. I'm saying I'm going to create equations for a, b, and c such that I'm getting rid of all the terms lower than delta x squared in this Taylor series, getting them to disappear except for exactly the term I want. Okay? The way to write that is like this. So I look back, the thing's multiplying f of xn, a plus b plus c, I want that to be equal to 0. Okay, so just jumping back here, a times f plus b times f plus c times f, don't want that to stick around. Actually, I'm just going to write this up here. Okay, so the terms that are multiplying f of xn, a plus b plus c, I want those to be equal to 0. I want the summed to be equal to 0. The second one, which is f prime at xn, I want that to stick around. In this case, it's going to be a times delta x plus c times delta x, or excuse me, minus. Gotta get my signs right. This marker is horrible. And I want that to be equal to 1, because all those terms are multiplying f prime, and I want that to exist. I'm approximating exactly that. The third equation is going to be multiplying f prime, double prime, of xn. So then I just look, see what's left over. Well, I have a times delta x squared over 2, factorial, and then plus c delta x squared over 2. And again, I want that to be 0. Okay. I have 3 equations. I have 3 unknowns. I can solve for a, b, and c. Now, you could ask, it's like, why stop there? Well, I only have 3 unknowns. But now this is starting to actually suggest that, well, if I wanted to actually get another order of accuracy, maybe I wanted to get rid of this delta x cubed term, I could add another unknown. Either I could add maybe f of x n minus 2 or f of x n plus 2. I get a, b, and c, and d. I just have to solve 4 equations, but I would do the exact same thing. So this is very constructive. And I would also see that, well, if I'm going to get rid of all these terms, then the things left over are hopefully only going to be delta x to the 4th. And actually, it's going to turn out to be 1 less than that, but as we'll see. Okay. Oops. Okay, to make sure I did this right. Okay. So if I just do a little bit of algebra, basically, thing to do is start here, solve for one of the a's or c's, plug it into this thing, get a and c in terms of each other, and then once I have both a and c, because these equations are just based on that, all 3 of them have to add to 0. And I have my solution. So this is what it looks like. A is going to be equal to negative c, just based off those equations. They're going to be opposite. And we're going to actually find out that b is equal to 0. So this is just deriving exactly what we've already found. But it's nice to just confirm this. So we know that c is going to be equal to negative 1 over 2 delta x, which means a is equal to 1 over 2 delta x. Now, just to complete the derivation, we plug in a, b, and c. And if we just do the algebra here, we find out, well, these 2 things are going to cancel like we want them to. These things are going to, with the 1 over 2 delta x piece, the delta x is going to go away, and I'm going to just get f prime, right, due to the fact there's 1/2 there. And then if I look at these 2 terms, the delta x is going to still leave a delta x, but they're all both going to cancel. And this is the kind of thing just to keep in mind. It's not that the leftovers are going to be delta x cubed. It's actually going to be 1 over 2 delta x is going to come into here and actually make this delta x squared so that we see something like this. Okay? So we have f prime, that's the thing we want, plus something else, and you see this is going to be delta x squared. And in fact, there are higher order error terms, delta x cubed, but those are shrinking even faster than this term. This term dominates the error. And then we can conclude that this is the case. Okay? So the nice thing I like about this as well is that you also explicitly see that, say, you were really lucky. What happens if f triple prime at xn was 0? Well, actually, that means that our error is going to go as delta x cubed. Okay, so that would be lucky. We know that's not going to always be the case. But we see exactly what the next order of error is going to be. And you can carry this on. Obviously, this is an infinite series at this point. Okay. So, we could do this again. If we take our first order forward difference, d plus 1, and the backward difference, and we average those two values, we end up getting the same thing. This doesn't generally work, but you can actually sometimes find out that the combinations of lower order derivative finite differences will actually give you a higher order one. It doesn't work too far further than this, but it is sometimes this is how people actually show that is, and you can just algebraically show that this is the case. But this is actually why we see the fact that if I shift my points that I'm evaluating the derivative at, this is exactly why that actually ends up working, because in fact I'm actually taking the average of those two approximations. First derivatives are great. What about second derivatives or higher order derivatives? Well, we can do this using interpolation, but you can imagine that this is going to get even more annoying from the interpolant standpoint. Take second derivatives, evaluate those. So again, I kind of like to do this using Taylor series again. We have the exact same setup. So I'm using xn minus 1, xn, and xn plus 1. I want a center difference. I can use 3 unknowns for this. Okay? So I'm going to give you a couple of minutes. Try to construct the system of equations, in which case what I'm going to keep is f double prime. Okay? So do exactly the same thing we did here, except in this case I want the second derivative. Now, you don't have to solve it. We'll talk about what it looks like, but see if you can set up the equations at least. All right, so I'll give you a couple of minutes for that. And then we will talk about the general scheme of things, some forward and backward differences. Note that you can also do this for forward and backward differences. You just change, maybe you don't use xn minus 1 and xn minus 2. So you still have 3 equations, 3 unknowns, that type of thing. And there's actually a way to algorithmically get this back out too. So give you a couple of minutes for just coming up with a system, and then we'll come back together and finish off the discussion. All right, what are these equations? What's the first one? A plus B plus C. And what's that equal to? 0. What's the second one? What's that equal to? 0. How about this one? A delta x squared over 2 plus c delta x squared over 2 is equal to what? 1. Yeah. Note that these are the same equations. I'm just changing what the right-hand side are. Okay. So this is general. Once you set up the equations for these things, it's obvious, the Taylor series are not going to change, and the ABCs are not going to change. So you can kind of do this however you want. If you solve these equations, you get A is equal to C. Okay, so this is a little bit different. And B is still sticking around, and it's equal to negative 2 over delta x squared. Now, this isn't a hard and fast rule, but generally speaking, when you go from first order, if you notice the first order derivative, the derivative is first order, not the convergence. The derivative is. Keep in mind there's two different things going around. Generally, you're dividing by delta x. The second derivative usually has delta x squared. In fact, the third derivative is going to have delta x cubed in the denominator. That's a consistency check, if you'd like. But here's just solving these equations and plugging them in. And this really actually did that funny-like. What we find out is that the approximation looks like the following. The eventual equation is going to be f of x n plus 1 minus 2 f of x n plus f of x n minus 1 divided by delta x squared. Okay. So there's a lot of consistency checks here. One, for instance, you can see I have 4 evaluations of f, but there's 1, 2 are 2 positive and 1, 2 are minus, so that actually is kind of important. And again, I'm dividing through by delta x squared. Units-wise, if this was, say, spatial, if I'm taking the second derivative of something, that had best be delta x squared. I have to have dx squared, means there has to be time or spatial units squared power in the denominator. Again, another way to check that this is true. Okay, so last thing to do really is just to check that this works. So this is all actually implemented. You can take a look at this. This is the vectorized form of this stuff. So this is the second derivative. So of course that's negative sign. It works pretty well even with a few points. But we also want to know what the convergence looks like. And it's doing what we expect. Somehow I changed colors, but anyway. This is just an example of where I'm not just using the first point. I'm actually making my red and blue lines go through a point that's not just that one. And the reason why is you can see that this is actually not quite converging at a linear rate. It's converging at a different rate. But once it gets down to about this point, then it's actually going down in a log-log plot like a line. And this is very common. Usually it takes a little bit sometimes for these things to behave asymptotically, right? The asymptotic statement really is that in the limit, we see the delta x squared behavior. So if you go too big, you may not see it. It might just be the error is way too big, or you just have the inconsistency. Okay. Second order, the second derivative approximations are all second order. Because of the fact that we need to go all the way up to delta x squared, we need to get that term to be 1. And then everything else left over is going to be of order delta x squared as well. Yeah?
Is there any significance?
Oh, that's completely arbitrary. Again, that's just how I drew the line. So this order C function, I used the second, 0.0, 1, and then 2. And so I just did that. Any other questions? There is a more subtle question about where it starts adding asymptotically. That's a much more difficult question. In fact, that's actually usually not possible to answer, except for very special cases. Any other questions? All right. Well, let's do the inverse. Let's do integration. There is a template up. one is this? Oh, ooh, that scared me. I was going to evaluate all funny like. Okay. Integration. We had finite differences for derivatives. We call integration, numerical integration, quadrature. The reason for this is that it's making quadrilaterals and adding them together. That's kind of where the name comes from. We do something that's a little bit more advanced than this, or we can if we would like to. But as you've learned in calculus, when you derive integrals, basically it's drawing boxes that fill in the area under curves. All right? Okay, but this is the basic goal. We want to approximate the integrals for lots of these things. Now, something to keep in mind here, derivatives are, by and large, fairly easy to do. All right? Would you rather be asked a bunch of derivatives to take of a bunch of functions, even as complex as they are, or would you want to do integrals? For me, personally, derivatives. Hands down, integrals are way harder. I don't know how many times I've been up in front of a big class of students and been asked an integral, and I'm just staring at it for like minutes, well, it feels like minutes, and I have no idea. All right, integrals are hard. They're very hard. So this particular topic is actually a little bit harder as well. There's all sorts of different techniques to it. It's a much larger set of questions. And this is just indicative, again, of the fact that derivatives are easy, so usually we can do those by hand if we have the actual functions, but integrals, not so much. So let's start. As I said, integrals are harder. Sometimes we just don't have closed form solutions. This one we can do. Kind of know how to do this one. But a lot of times we don't know this. And there's all sorts of cases where this can come up. This is actually would be a case where you were trying to measure the distance along a curve. So it'd be an arc length. Again, we can solve this one. But there's all sorts of other cases. ODEs are actually, you can just use numerical quadrature. If I integrate this thing twice, I can get out a solution dependent on whether or not it's dependent on you or not. We can also do systems of ODEs where we're going to actually make this even more complicated. And then we can solve via integration. So these three steps are, there's lots of assumptions going into here that I can come to this, but in essence, we may want to be able to do this as well. And of course, it comes up in PDEs. Same type of thing. What we're really doing is we're trying to invert an operator. In this case, it'd be del squared. We still have a time derivative on the left-hand side, but maybe we can somehow approximate the right-hand side of this equation in such a way that that'll work. So this comes up everywhere, not just solving hard integrals. The basics of the idea really come down to how we actually define the integral, either a Riemannian integral or a Lebesgue integral. Doesn't really matter. Both of them are very similar. We're going to say capital I is going to be equal to the integral we want. We're going to approximate it with something called capital I subscript n. N is going to be the number of pieces of the interval we're going to cut it up into. Okay? So note that the number of points that we're going to use is not going to be capital N. It's going to be capital N plus 1, because we have n intervals, n plus 1 points to do that. What we're going to do is we're going to evaluate or approximate these integrals by evaluating the function f, which we have, the integrand, evaluate it at a point xi, which I have not specified where that is. That could be anything. And I'm going to multiply by a weight. Okay? That's the general form of a quadrature rule. And then, of course, we're going to say that we have, or what we want is the limit is n, capital N goes to infinity, so the number of partitions. Usually we call these capital N things partitions. The more partitions we have, this should limit to the integral. And of course, if I'm careful about this, the Riemann integral pops out of this. Okay. So let's look at that, because that's kind of the most basic, most familiar piece of this. So we're given an f. We're going to partition the interval a to b, because that's our integral bounds, into uniformly spaced points, xi, and they're just going to be counting up. We just specified that. We don't have to make this uniform. This is completely arbitrary to that, but let's just say, for the sake of argument for right now, we're going to cut it up into uniform points. So somehow we're going to evaluate at some xi star. Okay? So this is some point inside of one of these partitions. So the xi's themselves now are a little bit different from what I defined before. They're just going to be the pieces that are defining each interval or each partition. Somewhere inside that partition, I'm going to have an x star. That's where I'm going to evaluate f. And then I'm multiplying by what is effectively delta x. All right? So this is the height of the box. This is the width of the box. Okay? The most basic type of integral. Okay? So how do we pick x star? Well, midpoint rule works. Just take the middle point of the particular partition, and we get back out something that looks like this. And of course, this works. We know this converges, and it looks pretty good. So let's try this. Oh, that's kind of entertaining how the little hats moved over. We can calculate this using a simple cumulative integral. So note that we're going to be very careful, or we're going to try to be very careful about this. We can't do indefinite integrals. That doesn't quite work for us. We can do this type of integral, right? Because this is giving you a function back out. That's actually a function of x. So you're going from 0 to some x, 0 to some more x. That's a cumulative integral. And you're finding the cumulative integral from some standpoint 0 all the way up to your value x, and that gives you your function. Otherwise, if we're doing from 0 to some other constant, that's one number. We can do that too. It's just a little bit less intuitive. So we're always going to be doing things like this, or just finding single numbers back out. Okay? So we're not just finding the antiderivative of a function. We can't actually do that. Well, we can if we're clever, and we're doing something completely different than we're going to talk about using computer algebra. But this is important. So for instance, in this case, what we get was if we actually did this integral, we know integral sign is negative cosine. We evaluate it from 0 to x. The 0 gives us 1, and it's minus cosine x. Okay? So if you're implementing these things or you're trying to measure these things, just remember that you might have a constant that has to come into it as well when you're doing this. Okay. So first thing we're going to do is implement midpoint rule, which is right here. So because this is our first one, I will write this one. Generally, the way, again, I'm going to kind of like notationally do this in the code is the hat is going to represent the approximation. And in this case, I am going to compute the cumulative integral. So that's why x star dot shape is going to be the set of values that I'm stopping at. So I'm going to go from x star 0 to x star 1. The integral between those two things is going to be a value. And then x star 0 and x star 2, I think about that, is going to be the next value of the function I'm going to compute. So what I'm going to do is I'm going to start out with the first value of this, the integral, and I'm going to just compute what this looks like. So delta x, we have a uniform partitioning here. We're not doing something fancier than that. This is the first integral, and I also know that I can actually do this simply because I know exactly what x star is. It's 0. Right, so that's why this looks a little bit funny. And then if I actually start the loop, so here I called num partitions is actually going to be that capital N. So I skipped the first one because I've already computed it, but the rest of them are going to be equal to I hat I minus 1. So the reason why I'm doing that is I'm going to compute the new value, basically the box in my new partition, and then I've already computed all the rest of them to my left, so I'm just going to add that to the rest of it. That'll give me my cumulative integral. That's why I look to my left value. And then I'm going to, again, do delta x. So I should mention, actually, kind of forgot about this. X star is way up here. I've already computed the midpoint of all these things. So that's just a thing. So x hat's actually the partitioning, the points of the partition. So if I did that right, oops, what did I do? Oh, for I in range. Oh. Okay, so there's a couple pictures here. The first one is kind of the one you see in calculus all the time. You can see this is the partitioning. You can also see that the function f, which is drawn here, it's using the height of the box based on the midpoint value. So that creates the box. So this would be the first value. It's this value here. This is the second box. This value here is going to be the sum of this box and this box added together. Similarly, the third value here is going to be this box plus this box plus this box, so on and so forth. That's a cumulative integral. Okay? So it starts getting negative when I start getting over here because I get negative values for this. You could also do an absolute value around this and get the actual area under the curve. So note that this is not the area under the curve, unless you really wanted to have it positive or negative. There's all sorts of things to question there. But this is the true cumulative integral, 1 minus cosine x, and we're basically right on top of it. And we're not even using that many partitions. Okay. So it works, but this is a very nice function. Okay, so that's the basic idea. And now we got to talk about error analysis. So we have this general quadrature scheme where we have a weight. So the last one, the weight was just delta x, or the difference between the size of the partition. And then we had some xi, which is going to be, in our last case, we said that was x star, but some value of x, the function evaluated at x. Okay, so how do we go from there to error? Well, we're going to say the true integral of f, so that's why we're using kind of this bracket functional notation. The true integral I is going to be equal to our approximation plus some error. Okay, so we've kind of said this before. So we're going to say that the degree of in is the integer capital N, and we're going to say that we're going to take a polynomial and find that the error actually evaluated at some polynomial is equal to 0. Now that seems really weird at this point, but if you think about it, what we're really doing is actually we're doing an interpolation. The last point was just a constant. We're just evaluating at some point, but we could actually extend that. If we reconstruct and integrate in between on a partition, do an interpolation and integrate that polynomial exactly, because we again know how to integrate polynomials, we are going to get another approximation. So again, we're going back to the idea that at the basis of all of these things is interpolation, and we know how to deal with polynomials. Okay? So that being said, we have an error, and we're going to say that error is going to be 0 for some degree of polynomial. Okay? Now, if that degree is infinite, that's not so good. But if the function f that we're integrating is a polynomial of some finite degree, there is going to be a pi such that I'm going to be able to integrate that exactly. And it's going to be equal to 0. Okay? So that's kind of the technology behind all this. And it's important that there exists, for some of the things we're going to say, there exists something such that this is true. Now, say, take sine and cosine. We know those are infinite. They can be represented as infinite polynomials. This still actually works pretty well. We can never actually make the error gets infinitely small, arbitrarily small, but we can eventually let n go to infinity and get back out the true solution of this. Okay. So that's how we're going to look at this. And due to that kind of idea, let's actually look at some different ideas and really broad classes of different ways to do this. The first one is Newton-Cotes. So we're going to use n plus 1 equally spaced points. So we're going to assume everything's uniform, and we're going to have a polynomial interpolant that is capital N. degreed. Okay, so basically what we've done before. We're going to evaluate f of x at these points and exactly integrate the interpolating polynomial. That is our quadrature rule. Okay? Now, we already know this might not be a fantastic idea because we've already said that having arbitrarily degreed polynomials may be arbitrarily bad. But the thing to keep in mind for all of this is that is the good one? Let's say we have this function again. All right, I used this before. We have points. Okay. What we're really saying here is we're going to pick a small number of points and find that the quadrature rule we're going to apply to is going to be on a group of points. So for instance, what we can do is say, I want 3 points, so capital N would be 2. So I'm going to use this interval. So that would be a partition in our language right now. Okay, so this is going to be a partition. We're going to interpolate those 3 points and integrate that polynomial exactly, which would be quadratic. We're going to go to the next 3. That would be our next partition. And then I didn't draw enough points, but you get the point. Okay. So there's 2 different things here. We have the partitioning, and we have the points that we're actually going to evaluate the function at. Okay? Now, usually when we're talking about quadrature, we have a function. That's not always true. We may actually only have data points. We still might want to integrate that, and that becomes a little bit more complicated. But just keep in mind that we actually do have 2 different things to play with. We have the partitioning, and we also have the data points. So what this is saying is that we're going to pick, per partition, we're going to pick some number of points, n plus 1. They're going to be equally spaced, put a polynomial between them, and then I'm going to integrate that exactly, and that's going to give me my rule. Okay? This is an incredibly generic thing to do. In fact, trapezoidal rule is a Newton-Cotes quadrature rule. It is the one that has capital N is equal to 1, so it's a line, which is, of course, the trapezoidal rule. So in this case, that was not this is a good green one. So the partitioning is actually going to be matching the data points. But what we're going to do is we're going to say, all right, well, trapezoid rule constructs that line, right? Constructs that trapezoid, and whatever the area of that trapezoid is will give me the value of the integral, or an approximation to it. So that's why Newton-Cotes, or trapezoid rule, is a particular case of Newton-Cotes. All right, so let's look at this a little bit more carefully just to make sure that we get back out the same answer. Here are the polynomial coefficients. We know this. We have the constant term, y-intercept term. We have the slope. This is the polynomial that we have. All right. Do a little bit of algebra. We have P0 plus P1. Right? We have to integrate this. Right? We're not just using the polynomial. If we integrate our interpolant, we get P0x plus P1 x squared over 2 minus xix. Okay? I simplify that down. I'm actually evaluating at the partition borders here in this case. Do some algebra, and I come up with trapezoid rule, which is exactly delta x over 2 times the sum of the 2 function valuations, or the way I look at it, it's the average value of the 2 function evaluations times delta x. Okay, so that actually gives you exactly, you have this width, and then you're using the midpoint, or not the midpoint, the average value of these 2 things, which would be like a box that looks like this downwards. Okay? And again, this is equivalent to doing polynomial interpolation. Okay. Last thing I want to say, so we've almost ran out of time. Oftentimes, these quadrature rules actually can be brought together, especially when you have uniform grid points. So trapezoid rule is one of the most common ones we talk about, and that just means that there's a commonality, right? I'm evaluating at this point and this point, and it gives me what I need here, but I've already evaluated this point. I only need to evaluate this new point, and so I can actually construct the quadrature rule, or the quadrature for this next thing by just adding in the appropriate thing here, which means that all I have to do is calculate the first quadrature, and the rest of them actually add together and simplify. This is very common for these types of things, and we'll actually see Tuesday how that actually can be really useful if I decide that I didn't use enough partitions and I want to increase the number of partitions without actually doing much work. All right, so have a good weekend. We will finish this up next Tuesday. The homework, if you want to do it over the weekend, look at the notes. All the information is there. A lot of this is just trying to implement various quadrature rules. If you have questions, please feel free to ask and put it on Campus Wire. Okay. I will see you next time.